Hello everyone. Today I'm gonna present to you our work about unified gradient reweighting for model biasing with applications to source operation. This is a joint work with Dimitrios Bralios and me, my advisor Smaragdis. So there are a few problems that we face usually when performing source operation or any other task, such as training any neural network effectively. So we can see here that the model can yield good results under expectation, but there are bad examples or difficult examples that for the worst case scenarios, our model fails miserably. And also the variance is another thing, the variance of their performance as we see here. Another problem is that obtaining state-of-the-art results with models presented in the literature might require significant computational resources. For example, you might need to be training the model on many days on a single GPU to obtain those kind of performance. So the best results on average might not be what we actually need. You can think of an example where we have a speech denoiser that we effectively need to perform very accurate performance, to have a very accurate performance on our voice without actually caring for all the other voices, all the other types of sources. But what can we do with the limited capacity networks that we have nowadays, and what can we do with all those problems? So bias is a huge problem in neural network training, and there is also the trade-off, the bias variance trade-off. So high bias means that models are effectively underfitting the data set, while the high variance means that we have an overfitting model where one small perturbation could effectively lead to a miserable, to very bad estimation at the output. So many other works in the literature focus on making neural networks unbiased. And others are actually trying to make the neural networks more robust during training by providing adversarial examples or data augmentation in input data and so on and so forth. So in this work, we want to see how can we use the bias during training in order to train a neural network with limited capacity to fit the most valuable information for the specific task that we want to. So what we propose is that we should focus on specific examples during training in order to shift the operating points of those estimators in the case of transpiration or other estimation tasks. Or you can think of it as how you actually define the most favorable functionality of your neural network. What do we mean by that? So for example, you can think about having a neural network being very robust on hard examples, so perturbations of your input, or make the convergence of the model really faster through curriculum learning or any other method. And one more thing that we focus here on this study is that we can make more accurate predictions for certain types of classes that we're mainly interested in. So the way that we propose to do that is that we actually reweight the gradients during training, and we bias the model towards those examples which would make these modes which would help us solve those problems. So in a conventional mini-batch SDD parameter update, we take the gradient with respect to some loss, as we see here. And then we update those parameters, assuming that those updates provide an unbiased estimator of the true gradient. And as a result, of course, all those examples in the batch are weighted equally, as we see here, because it's an expectation under a uniform distribution over the examples in the batch. So our idea is very simple. We want to reweight those gradients with a more expressive probability distribution. and we can let the user define this probability distribution over the batch, and we can give the flexibility to focus on the examples that they provide the more information with respect to the task or the mode that we're interested in. So another question that arises now is that, okay, we'll let the user define any probability distribution as long as it is a valid one, but which probability distribution is good? So we provide one simple parameterized gradient reweighting scheme through a softmax distribution using our weighting function, as we see here, that can also be time varying. So the iteration index k indicates which step we're in the training process, and we can do that for all the examples in the batch. So we see here what is the output of this probability distribution with respect to the ith example in this batch. And we will see later how we define this probability distribution, but this weighting function in order to parameterize this probability distribution. But this is the overall form, which is very general, very easy to implement, and computationally efficient. We follow a source operation setup in order to show how we would solve all these problems that we referred for source operation. We use, as audio data collections for speech, we use utterances extracted from the Wall Street Journal corpus, while for the non-speech environmental sound classification, we use the environmental sound classification ESC 50 collection for non-speech dataset. We always consider mixtures of two active sources. We extract 20,000 training mixtures with online augmentation, 5,000 for validation, and 3,000 for testing, while each one of those mixtures are 4 seconds long. And we mix those sources with uniformly sampled SNRs from -30 to 30 dB, covering a wide range of conditions. So we see here that as a separation network, we are using the pseudo-MRF architecture, which provides a good trade-off between computational resource requirements and actual separation performance. As a loss function, we use the negative permutation variance scale invariant signal to distortion ratio, which is also used in model center literature, and this is a signal level loss function. And as an evaluation metric for each one of the sources, we compute the SISDR improvement over the input mixture. So we're going to see now how we configure this weighting function for our gradient reweighting scheme. So effectively, how this F is defined in order to solve different problems. So in order to provide more robust estimation, we use this weighting function. We use the robustness parameter alpha, and we multiply it with the loss function with respect to of our estimated sources here and our clean sources here. So this is the signal level loss. And when we have an alpha, which is while we increase alpha, we see that we put more weight towards examples with high loss. So when we do that, what happens is that the model focuses mostly on difficult examples, which cannot obtain a low loss. In the opposite, we can do curriculum training by focusing more on easy examples in the beginning. So now instead of the alpha, we have a beta parameter, which is also parameterized through the iteration index k. So that means that we can change beta through time, and we can effectively want to put more focus on these examples in the beginning, and then go to a more uniform distribution. Also, we can choose a weighting function with respect to some kind of static gamma, which is only parameterized with respect to the class of sound that we want to separate, as we see here. So we can we can focus on, we can put more weight on some classes of interest that we want to separate and we want to be more accurate on, and we can neglect other types of sources. So in our results, we see that for the first experiment, we can see that, again, as increasing the alpha here, we can obtain, we can significantly reduce the outliers. So we can push this this distribution to be more compact, to have like less variance, as you see here, by weighting more the difficult examples. And here is another question now, like everybody in source operation is reporting mean performance accuracy, which you don't actually know if this is your best metric that you want to pay attention to. So for example, in a case that we have a system, or we have a specification that we cannot tolerate extreme failures, the mean is not the appropriate metric. So we see here that if we consider the quantile, the first or the fifth quantiles, we can significantly improve the worst performance by just putting more weight on hard examples, and then letting the model focus more on those kind of examples. So on the opposite, we can perform curriculum training again with the same reweighting, simple reweighting scheme. So by using the time varying beta, as we see here, which asymptotically goes to 0, while initially puts more weights on easy examples. So we see that compared to the baseline, which we have a uniform distribution over all the gradients in the batch, which is the red one, we can obtain better convergence in terms of the mean SISDR improvement. And as a final experiment, we have a sound separation model trained on both speech and environmental sounds, and mixtures of those two. And we evaluate our model on speech, environmental sounds, and the combined 50-50, let's say, case. And we see what happens. And we do that by just using our simple reweighting scheme, where we just use a parameter gamma to say which class of sound is more important for our case. So here, for example, we see that if we are more interested in separating speech and being more accurate, we can have a higher weight on speech, and then obtain better results compared to the baseline, of course. And of course, we can do exactly the same thing for the environmental sound class by just doing the opposite thing. So in order to conclude, we have presented a simple but unified gradient reweighting scheme, where we let the user define their probability distributions over the batch in order to train their model. And this can be implemented with negligible computational cost. Moreover, we have shown from our results that we can solve real-world problems appearing in separation models, but this could be potentially extended to many more tasks or even other domains. So in our experiments, as we have seen, we can adjust the trade-off between the robustness and the mean estimation accuracy, and we can make the models converge faster by performing curriculum training, again through this reweighting scheme. And as a final thing is that we showed that we can steer the model and we can make it focus more, producing more accurate results or reconstructions for sources of specific classes of interest. So I would like to thank you very much for watching the video. We will be more than happy to see everybody in the Q&A session. And you can also find the link for the code online. Thank you very much.